Welcome back, students, to Chapter 5, Chemistry 1510 video notes. Let's talk about kinetic molecular theory. So the kinetic molecular theory is a theory of gases and how the molecules move and behave. And so when we talk about an ideal gas, these are the rules that ideal gases follow. Now, we assume that ideal gases follow all of these rules, but in actuality, some gases are better at following the rules than others. And these rules aren't always true, but we assume that they are because it makes the math easier. And so let's talk about these rules one at a time. So first of all, when we talk about the size of gas molecules, a lot of times when we draw our containers of, solid and liquid, right, that takes up the space of the container, and then the gas, I guess it should be a closed container, right, has something like this. Now, these are the types of pictures you've seen since you talked about these ideas in, middle school. And when we draw the gas container, we're drawing these small dots to indicate gas molecules or particles. But the problem is even though they're, pretty small, they're not really a good model of the size of the gas molecules versus the distance between the gas molecules. So one analogy is if a gas molecule is the size of a marble, then the container that it's taking up would be the size of a football stadium, right? So their size is so small, it's negligible compared to the distance between the molecules. In addition to that, we see that when we're talking about gases, the gas molecules are going to move randomly, right? So there's no order to them, and they're going to move in straight lines. And they're moving in all directions. And when we say straight lines, what we mean is, the pathway of a gas particle isn't going to curve, right? It's going to be going straight. Now, when we talk about gas particles, particles tend to be either attracted or repelled by one another, right, depending upon their charge. But when we talk about gases, the forces of attraction or repulsion are very weak because the distance between those molecules is so great, right? So there's a great distance between molecules. So think of you, right? Here's you. Oh, that was an ugly head. Let's try that again. There's you. And there's your chemistry friend. And you're on opposite sides of your chemistry classroom. And you're holding a magnet and they're holding a magnet. And you're 30 feet away from one another. Those magnets are not going to be attracted to each other. They're way too far apart. Right? And so the gas molecules are going to be like that too. Whereas if you and another chemistry friend are really close to one another, like inches, then maybe your magnets are going to feel that attraction or repulsion between each other. So when the gas molecules get close to each other and they collide, that's when they're going to feel the attraction or repulsion between each other. But in general, they're too far apart to feel that attraction or repulsion. So let's talk as well about that collision. So when things collide, imagine you have a wall and then you have slime. Slime's apparently like the new thing with kids these days. They really like making slime. And so that's your blob of slime, and you take that blob of slime and you chuck it at the wall. when you throw it at the wall, what's going to happen is the slime's going to go plop, right, and smack up against the wall and just kind of ooze down the side. Right? That would be considered an inelastic collision. Whereas an elastic collision would be if you have a ball and you have a ball and they hit each other and then they bounce right back. Right? Or maybe even better yet, you have a wall and you have a ball and the wall, wait, I almost said the wall hits the ball. The ball hits the wall and it bounces right back. Right? So that would be more of an elastic collision. We're not going to get into the whole, physics. Yes, you lose some energy, friction, whatever, because we need to make some assumptions, right, that these are elastic collisions or else the math gets a little bit too complex for us. So we're going to assume that when the molecules collide with one another, they're elastic. So it would be like if you have ever played, what is that sport? I'm not going to remember it now. So let's just pretend we're playing with a tennis ball, right? And the tennis ball whaps against a wall and comes right back at you. That would be like what your molecules of gas are doing. And then the final thing in the kinetic molecular theory is that the kinetic energy for the molecule is proportional to the temperature. So what does that mean? It means higher temperature, higher kinetic energy. And remember, kinetic energy is kind of the movement energy, right? So this would be if you have a higher temperature, your molecules are going to be moving faster. And then the reason this becomes so important when we talk about gases is because if your molecules are moving faster, they're going to bump off the sides of the walls more often, and that's going to create a higher pressure. So that's why one of the reasons why we're going to see a relationship between a higher temperature creating a higher pressure. And then this is really interesting, is that all molecules, regardless of their mass, have the same average kinetic energy at the same temperature. So what that means is if the temperature is 25 degrees Celsius and you have a bigger molecule versus a smaller molecule, they're going to be moving at the same, have the same kinetic energy. And now it's the average, right? But that's okay. We'll just say same kinetic energy for the moment to make it a little bit more simplified. So that's enough with kinetic molecular theory of gases. We'll see how these get used throughout the gas chapter and in our subsequent sections. So thank you as always for your attention. This is Katoni signing out.